Saxon Algebra 2, Lesson 62. I am here to have a fun little chat with you today. Cross off Lesson 62. I cross off before I even teach it. That's how confident I am that you and I are going to spend a little time together chatting about this subject. Complex roots, specifically complex roots of quadratic equations. Okay, what in the world does that mean? What I mean is that sometimes, whether we are completing the square or using the man-eating dragon, it doesn't matter which. Today we're going to complete the square, sorry. Sometimes we will get, for our answer, complex numbers. Remember, roots is just another word for answers. It's okay. It's perfectly fine when that happens. We just have to remember how to handle those complex numbers when they come up. So I'll remind you of all those rules. Let's dive in, 62.1. And here's one thing I will tell you about these problems that yield complex roots is you don't always see them coming. Now, this one's a bit of a mess, so let's clean it up first. Right? Everything's on the same side of the equal sign, so I'm just fixing the order, right? X squared, plain X, plain number. This looks innocent enough. There's nothing in this quadratic equation that would make you think it was going to cough up such an unholy terror as imaginary numbers in our midst. Remember, complex numbers are when you have a real and an imaginary. So somewhere in this, we're going to run across some imaginary numbers. Heaven help us. You can't tell in the beginning, right? So don't worry about that. Like a lot of things in math, just decide on your process, buckle in, and see what happens, right? So we're going to use completing the square. You don't have to use completing the square. We could use the man-eating dragon. John just thought it would be great fun if we did some completing the square problems because then we can practice that. But if you chose to do man-eating dragon, aka quadratic formula, rather, that's the quadratic formula, that works perfectly well too. I call it the man-eating dragon. I will tell you the reason why. Many years ago, I was teaching this class to a group of students, and we met at a building, Edmonds Heights, for those of you who know. It's a school for homeschoolers, and we met in like a standard classroom. But we met just after lunch, and the classroom was empty, so my students would often, there was like 6 of them, they would go and eat, and they were all friends, they would all go eat lunch and hang out together and wait for me to come. I came in right at 1 when we would start teaching class, and they would all be there, and they'd throw away their lunches, and we'd go. So they were just sitting around, hanging out in lunch, and one of the boys, named Zach, started drawing on the whiteboard, and he had a bunch of different markers, and he made the most amazing dragon. He drew this really cool dragon, and coming out of its mouth was like a cartoon bubble, only it was like made of flames. He used orange and red to make the like cartoon bubble look like it was made of fire. You know, he put like flamey edges all around it. It was really cool. And I came in the room and I was looking at his dragon. I'm like, wow, that is so freaking cool. How did you draw that? And I'm like, my only question is, what's coming out of his mouth? Like, what would a fire-breathing, man-eating dragon have to say? And Zach looked at me, smiled, and went to the speech bubble of flames and wrote this. He wrote the quadratic formula into, it was like this. Only it was way cooler, right? The fiery flames of dragon fire. That didn't make sense. It was really cool, right? But it came out of this, and then the dragon was down here. And so in that class, we started calling the quadratic formula the man-eating dragon at all times, because it kind of makes sense. I mean, if something as evil and vile and torturous as a Man-eating dragon were to come to life, he might speak words like this in his flames, right? It's frightening. So I always call the quadratic formula the man-eating dragon. That might confuse you, or it actually might help you remember it. But that's a story for a different day, because we're not even going to do this. We're going to complete the square. And that just makes me think of the mathematicians of the 1600s going, ugh, we hate completing the square. It is so tedious. It is so boring. It is so many steps. Let's come up with a better way. And they're the ones who invented this. Oh my gosh, it's so cool. But we're going to complete the square. So the first thing we have to do is get the x by itself. So I'm going to divide every one of these terms by 3, even this one, which I've told this story too. I used to think that seemed so wrong. Dividing 0 by anything is just going to give you 0 back. It seemed like I was ruining my equation, but my teachers assured me that I wasn't. Okay, this cancels. That's what we wanted. Now we have x squared. I'm going to turn this one into a fraction because it's going to help me with my magic number creation. And then I'm going to kick that to the curb. I'm going to leave a nice gap there, minus 5 over 3. Now it's magic number time. Remember that when our magic number is or our b value is a fraction, instead of dividing by 2, we can multiply by 1/2. It's the same difference. Dividing by 2 is the same as multiplying by 1/2, so I just adjust my calculation so that it's more logical for me, if it's a fraction or if it's a plain number. All right, I draw the arrow because I'm going to need this number later. But let's figure it out. It would be minus 1 over 6, and then I need to square it. So that's 1 over 36. And it's positive because I squared it. And so then I have to add 1 over 36. I'm squeezing it because I want a little bit of room to adjust that fraction. All right, this now becomes a perfect square, and I'll write it the long way. It's going to be x. This is what goes inside of it. X minus 1/6, x minus 1/6. I write the same thing twice. That's the whole point. We're completing a perfect square, and our magic number is what makes the perfect square. All right, then I can test. This times this should equal this, yes. This plus this gives me minus 2/6, that equals minus 1/3. Check, it works. Now I can collapse that x minus 1 over 6 quantity squared, right, because that's what this means, equals, now I better fix this. I'm going to have to multiply by 12 over 12 to get the 36, right? And that becomes, I'll write it again, it's minus 60 over 36 plus 1 over 36. So that gives me minus 59 over 36. That minus sign is the first hint we get that complex roots are in our future. You don't have to recognize it, but if you're looking to pay attention, that's when you know for sure it's coming your way. All right, so now we're going to square root both sides. That makes everything happy over here. X minus 1 over 6 equals, now we know it's going to be plus or minus. We better write that in right away. I just taught the Algebra 1 kids about that. The top we can't help. The bottom's a perfect square, so we can fix that right away. So I'm going to put it over 6. But this becomes square root of 59i, right? Remember our rule that we separate the 59 and the minus 1, and then this equals I. Thanks to our friend Euler, who decided that this was a problem and it needed fixing, and this is the way he chose to do it. We just recognized that the square root of minus 59 is not a number you can find on any number line. It's not a real number. It is an imaginary number, and we designate it that way by writing the I after it, right? Okay. So now we're almost done. All we have to do, we can't bring this down. We can't reduce that. So our final step is to add that to the other side. 1 over 6 plus or minus the square root of 59. The I does not go in the pig house. It's outside of it. Over 6. That is our final answer. Notice if you will, that we used the proper form for a complex number. Remember that a complex number has two parts to it. It has a real part and an imaginary part. And you want to preserve those as two separate beasties. And that's what we did here. This is the real part and this is the imaginary part. And even though the fractions are the same, the denominators rather are the same, and technically we could bump them together if we really wanted to, we don't want to. We want to keep them separate because that's the way that we state a complex number, is we make the real and the imaginary very distinct and separate. Okay, that's our first problem. This is the right answer. Got it? Yes, teacher. Oh my God, I heard you. That's so cool. You're so far away and yet I heard your voices. In chorus. One more problem. Ready? Solve. Once again, John gives us the most innocent looking little numbers, although he does make quite a mess of it. All right. I'm going to fix this. Minus 2x. And you know, this plain number variable has already kicked himself to the curb. So I'm just going to leave him over there. I don't need to drag him back and then throw him back across. Poor guy has suffered enough. So I make sure these signs all look good. I just rearrange those. He is definitely the plain number. There's the x squared. There's the plain x. He's the plain number. He's kicked to the curb. It's all good. He'll be fine. Sometimes I think he's smarter. He stays out of all the drama of this side. First step, get rid of this coefficient. So now we have x squared minus 2/5 x. Again, I like to extricate that so that my magic number calculation is good to go. Equals minus 3/5. Magic number time, take b, minus 2/5, multiply it by 1/2, square it, take that. Now, we can cancel these 2's, can't we, before we multiply? So we can do that. So that gives us minus 1/5 squared. So I'm going to add 1/25 to both sides. Okay? If I wouldn't have caught that and I would have multiplied it, it just would have made a messier number because I would have had 4/10. Ugh, that would have been a mess. So it's easier to reduce, cancel, whatever you want to call it. Technically, this is canceling. Go ahead and do that sooner rather than later, all right? Then I draw my number, my arrow, I drew it to the new number as well. Okay, let's check and see if we did this right. X minus 1/5. We're saying that's the binomial that makes the perfect square. These two should multiply to this, yes, positive 1/25, and they should add to this minus 2/5. Yes, we got it. All right, so then we can rewrite this as the perfect square, x minus 1/5 quantity squared. Now we'll have to fix this side. This one we're going to have to multiply by 5/5, and we get minus 15/25 plus 1/25. Oh, do you see it happening? That becomes 14 minus over 25. There's the trouble. Square root, x minus 1/5. These two cancel each other out. The bottom is a perfect square, so that turns into just a plain 5. We add the plus or minus thingy because we've taken the square root, and this becomes square root of 14. The minus 1, the root of minus 1 becomes an I, imaginary number. And now our last step, we kick that 1/5 to the other side. It turns into a positive, plus or minus the square root of 14i/5. That's our final answer. Sorry, I overlapped. We keep them separate because we want that A plus BI format. Remember, this is the real number, and this is the imaginary. Imaginary numbers cannot be found on the number line. Right? Interesting. I mean, I'm interested. I don't know. You probably just wish it was time for this lesson to be over so you could go watch a YouTube video or eat dinner or go pound your younger sibling on the head. That's violent. I was just talking about fighting with my brothers and throwing snowballs with one of my students. So I've got sibling violence on the mind. Don't beat your siblings. At least not that hard. Don't leave bruises or marks. That will really get you in trouble. And if you are a younger sibling, oh, you guys are. My in-person students both have older siblings. One is the youngest of 4. Yikes, you better run fast. 2 of them are girls though, that's not that bad. I had all brothers. All right, now I'm just rambling to make this lesson last longer and no one needs that. 62 is over. Thank you, goodbye.